Good day, everyone. This is Jamal, and today we'll be finalizing our results of the 3 by 3 magic square of squares. This is the last goal I've set for my paper, so I'll share it with you, and you see I'm virtually done with the paper now. Uh, yeah, so this is all that is left, searching for integers for I squared. So this is my goal right now. And so, like I did before, we're just going to, I'll just use AI assistant to generate the codes to run inside SageMath. It gives the answers. We create our magic square to test it, and then life goes on. So yeah. So this is what you're going to do. You come to search for integers for I. So I don't know. What am I saying? Yeah. But what you're going to do is this. Uh, we just go here. Just go here. Remember this guy. Yeah. So um, we are going to take this formula for I squared. I squared. Uh, this is the formula, and then we just use notations that makes it easier for the computer. So let R subscript 2 be equal to M, R subscript 3 be equal to N, and then yeah, you see that generate SageMath codes to search for integer values of k for which integer solutions to m, n, and I are yielded. That's all we've got to do. So it's generating the codes. Okay, it's done. So what you're going to do is that you find out that the ranges provided are very small, too small. So we'll just change that. So we come down here, so we can just see the maximum length, the maximum size of key. Let me just see, 10,000. Yeah, and make this 100,000. You know, 10,000, 100,000. Oh, okay. Let's see. So let me see whether this works. Uh, yes. So I'm going to run it in SageMath. So I'll have to open a new file. Wait a minute. So let's see. Let's see what happens. Um, so far nothing. Or for convenience, we can just reduce. We can just make the max 10,000. Let's reduce the size, set sizes. There's some of the computational constraints. So we'll bring k down. We'll bring k to 1,000. I'm just adjusting so according to the limits of this computer. So 10,000. Let's bring this to 1,000. Hmm. Hmm. Okay, let's see. So I've reduced it so that K is 1,000, between 1 and 1,000, M is 10,000, N is 10,000. That's a decent range. Anyone with higher computational power can look higher, maybe up to a million, up to a billion, but you're just looking at what this computer can handle right now. So, and even with this, let's see if we would even get integers for I. So far, no numbers have been returned. Mm, mm. So far, nothing. Hmm. It looks like it looks like it's still heavy work. Wow. You know what? Let's try something. Let's try to read the ranges down to 100 and M to 1,000. This one doesn't go. I don't think anything else would ever. Let's see. But I mean, if this work works, if it doesn't work, actually would have to look higher. With bigger computational resources, much more than this MacBook. So let's bring it down. 1,000, 1,000, 1,000, 100. Because K100 should be easy. M should be 1,000. K should be 100. See, no one like it. So for we don't get integers. So right now, what we'll do is I'll put this code into that section for I squared. So yeah, So right now, this is what you have. You have not had any results and solutions yet. Let's see. Super nothing. But then now we can understandably remove this subsection. So yeah, I think I think that's just the paper. I think that's just the paper. Is it? I'll put it on picture. Yeah, yeah, yeah. So right now the goal is right now we are technically done with the paper. So the goal is now to find out, okay, fine. Especially those where we have all eight perfect sums. Which ones have near integers for the for those that are non-integers. So I'm coming. So we are going to search among these ones. Whichever ones are near integers, point zero something, would highlight it. Would slash text bf. We'll just highlight it. So, I mean, okay. So let's do this text bf. So we now see that we highlight it now. Let's highlight 349,924. No, not this guy. 318,244. No. So we have six integers in this one. And then for E, let's see what the square root of this one is. 250,9456. Yep. Okay. I think I should move this. No, let's look at this. I think this guy was an integer before, was a near integer. Now let's go here. think this one, I think it should be a near integer. 1503468363324. Yes, this is accurate. Yeah, that's a near integer and 00 there. So let's see. Let's test this one too and see. 757359504 144. Okay. 144. It's only to one. It's only has 10 after the decimal point. Let's see. 04. So let's try the other one. The middle center for E squared. 75735935797904904. No. So six integers, two near integers, and then one actual non-integer. Let's try this and see. So we are now doing this one right now. 507 957 137 608 498 7161. Let's see what we got. Nope. No, no, no. Never close. Let's do this. We are now going to test this one and see. 253978661 889 3012 to non-integer. So let's do this. We'll verify this one. Okay, yes. This also have a near integer as well. Wow, nice one. 4168 2615 608 1849. Mm-mm. Oh wow. Let me try a little sentence. I'm now here. This is where I am right now. So I'm trying to square root this one. 4168 0288 547 2305. Now I'm doing this one 375 867 090 756. Yes, looks like something else. So it's also a near integer. Wow, it's looking good. Now we'll square root this and see. So this is also 0.02, or label it or consider it a near integer. Now I have to square root this. Okay, this is also point zero. Yeah. So, so we have now. Okay. So we'll test this one and see whether this one is also a near integer or not. 6816 235537. So it's not a near integer. It's not a near integer. So let's try square rooting it here and see what happens. Also not an integer. So yeah, let's try this one. This one was the other time I tried was this was close to an integer. I think two or three zeros after the decimal point. So let's try that one. 35187 4376 12345. So, wow, this is the closest thing to a near integer I've seen among my values so far. This is a near integer. Mhm. That's nice. Let's see what the other guy has to offer us. 1759 373 4319 6082. No, not quite an integer. Um, let's share these guys. 1759 759. I think C2 also qualified for that. Oh, wow. Let's see. I'm trying to contemplate which one could I have missed out. Mm, mhm. Just like, okay. I think we've been able to do it now. So far, I think we are done with the paper. If anything, it has to do with number of equations somewhere. Let me see. I think we are done with this video. I think so far I've been able to get all eight sums. I mean, we've been able to get all eight correct sums across sides. Some we've been able to get six integers. And out of the three remaining non-integers, we have about, two being non-integers, near integers, and I've been able to build a framework or suggest a framework with which we could expand higher, you know. Probably if we are going to be very ambitious about getting all of it, maybe for the remaining uh, formulas for unknowns like g squared, c squared, maybe e squared and I squared from page 11 and 12 over here. One could decide to use computational searches as far as we go to find out, for example, whether we can have a system of two equations like g squared and c squared, and based on the resulting solution, we substitute and we can get 7 out of 9, or three systems of just equations that can work out, and we go from 5 to 8 or 6 to 8 integers. And so right now, I think this is where we'll leave this video. And I think we're done with the paper. So I'll put this paper onto Figshare, and then I'll look out for expect feedback. Just thanks for watching and ciao. See you next time.